Okay, I welcome you all to my video lecture presentation. Myself, C. Ashok Kumar, Professor, Department of EEE, and my course name is Electron Device and Circuit, and my topic for this video lecture is PN Junction Diode-2. And the overview of my presentation will be going on like this. First, I'll be explaining about the diode operating conditions, particularly I'll be concentrating the reverse bias and the forward bias. And next, I'll be explaining about the volt ampere characteristics. Okay. And finally, I'll be recapping the things, whatever I discuss. So first, already in the last video lecture, I said about the first operating condition that is called as a zero bias. So as already said, under zero bias, a depletion region will be created. A depletion region will be created at the junction. Okay. So that will be, we need to take it as a reference. Whenever you are going to know about reverse bias operation, we need to know about the status of operating mode of zero bias. Let us go into it. So as you can see here. So at zero bias, the barrier potential is created with a voltage of V0. And the situation will be like this, as you can see here. So this is related with the negative charge, that is due to the acceptor ions, and this is a positive charge, that is due to the donor ions. So a depletion region is created at zero bias. That you need to know. Let us go to our reverse bias mode. So here, so reverse bias mode. Reverse bias mode means, as you can see here, this is a P region and this is a N region. This is a P region and this is a N region. So P is connected to negative terminal of the battery, and N region, that is N, is connected to positive terminal of the battery. In a reverse manner, P is connected to negative terminal of the battery and N is connected to positive terminal of the battery. So this is a mode of connection in the reverse bias operation. Okay. So we know that under zero bias, a depletion region is created. So depletion region width, let us take like this under zero bias. That means here this side 2 positive ions and this side 2 negative ions, like that. Okay. At zero bias, this is the situation. So after that, here I am applying a reverse bias mode of operation. That means P is connected to negative terminal of the battery and N is connected to positive terminal of the battery. Now let us check the status here, how the holes are attracted and whether holes are attracted or repelled and electrons are attracted or repelled. Let us check here. So in the P side, what are the majority carriers? Holes. These are the holes. And in the N side, the majority carriers are electrons. Okay. So here P side, the majority carriers are holes. That means a positive charge. So that is connected to the negative terminal of the battery. So this is positive charge hole and this is a negative terminal. So what happens here? Attraction happens between this hole of P region and the negative terminal of the battery. That means the holes wants to move away from the junction. This is a junction, right? So they want to move in order to come out of the device, in order to reach the negative terminal of the battery due to attraction, opposite charges. Okay. So this hole earlier, this particular ions are covered with holes. Let me draw that. Okay. And here this particular donor ion is covered with electron. Okay. So whenever you are going for the reverse bias operation, so due to the attraction of holes with the negative terminal of the battery, what happens? So this hole earlier it is covered with this negative ion. So this hole comes out of this particular negative ion, which is acceptor ion. Earlier it is covering this one. Now whenever it is coming out, of that in order to reach the negative terminal of the battery, what happens? This will be uncovered, and this ion also will be uncovered. That means this earlier it is covering, now it is coming out in order to reach the negative terminal of the battery. So that's why here, as you can see, this negative ion which is uncovered, this is uncovered, this is uncovered, this is uncovered. Okay, so this is a situation of the ions. Earlier they are uncovered, earlier they are covered, now they are uncovered. Okay, and what about the situation of this particular column? Earlier they are covered with free electron. Now the electrons are getting attracted towards the positive terminal of the battery due to the attraction. So that's why here all the electrons that are in the N side, they wants to move away from the junction and they want to come out of the device in order to reach the positive terminal of the battery. So in this process, what happens here? Earlier it is covering here this free electron, now it is coming out. So that's why here this particular donor ion is uncovered here. This particular donor ion, once again it is uncovered. This donor ion is uncovered. This donor ion is uncovered. So in this way, what happens here? The depletion region is going on increasing. Okay, earlier I said at zero bias, let the width of the depletion region is W. Okay, now after the application of the reverse bias, okay, all the holes wants to come out of the device in order to reach the negative terminal of the battery, and electrons wants to come out of the device in order to reach the positive terminal of the battery. So in this process, they are leaving their ions uncovered. That means the depletion region is increasing here. At zero bias, the depletion region is W. Now it is increased to W dash. It is increased. Why? Because we are applying the reverse bias. Okay, whenever you go on increasing this applied reverse bias, the width of the depletion region is going on increasing. Okay, and what about the conductivity here? The majority carriers, they are coming out of the device, they are not crossing the junction, they are coming out of the device. As you can see here, the holes are moving away from the junction and electrons are moving away from the junction. So here no majority carrier crosses the junction. Okay, so that means the majority carriers does not participate in the process of conductivity of the PN junction diode. And what are the remained charge carriers? Those are nothing but the minority carriers. Suppose if you take this P side, minority carriers are electrons. As you can see here, this is electron. And if you take N side, the minority carriers are holes. As you can see, the hole is there. So this hole, it is N side is connected to positive terminal. This hole, and this is a positive charge. Due to the repulsion, it won't move in this direction. Instead of that, it moves towards the junction. Similarly here, if you take the P side, the minority carrier is electron. So electron, the P side is connected to negative terminal, and this electron is negative charge and this is a negative terminal. Repulsion happens. That's why this electron won't come out of the device in order to reach the negative terminal of the battery. So only option left to this particular electron is it has to move towards the junction. Okay, so the minority carriers cross the junction here, whereas the majority carriers, they does not cross the junction. So whatever conductivity happens inside the PN junction diode under reverse bias, that is only due to the movement of minority carriers across the junction. Okay, that is due to the movement of holes from N side to P side. That is due to the movement of electrons from P side to N side. So minority means, as you know, very lesser number. So that's why whatever the current that happens with the minority carriers is very small. Okay, so that's why here, as you can see here, only the minority carrier flow is there and the majority carrier flow is equal to 0. Majority means the current due to the movement of majority carriers. Why? Because majority carriers are not crossing the junction, whereas the minority carriers are coming to the picture by crossing the junction. That's why a smaller current will be flown under reverse bias. And as you can see here, the applied reverse bias voltage VD supports the depletion region to grow further. Okay, this applied reverse bias voltage is supporting the depletion region to grow further. If you go on increasing VD, the depletion region goes on increasing. Okay, which in turn decreases the current through the device. Okay, only one current that is flown in the reverse bias is due to the minority carriers movement, that is very small. That's why here IS is existed in the device, that is due to the minority carrier flow, and I majority will be equal to 0. And this is a notation here. This is a applied reverse bias voltage, and this P is connected to negative terminal of the battery and N is connected to positive terminal of the battery. Okay, so finally the concluding statement here is, in the reverse bias a very smaller current will be flown, that also due to the minority carrier flow. Minority carrier means very lesser number, that's why the current happening with this movement of minority carriers is very small. Next, let us move to the other operating mode, third operating mode, that is called as a forward bias. So forward bias means, as you can see here, the P is connected to positive terminal of the battery and N is connected to negative terminal of the battery. That is called as a forward bias. So once again, when you go deep into the operation, you need to know about the status of the PN junction diode under zero bias. Okay. Let us see the diagram once again, zero bias diagram. So this is the diagram. As you can see here, two columns of negative ions and two columns of positive ions are there, which is the creation of a depletion region under zero bias. Okay, forward bias. So forward bias, I am applying a forward bias voltage VD. That means P is connected to positive terminal of the battery and N is connected to negative terminal of the battery. Okay, so by this application of this forward bias voltage, what happens inside the device? As I already said, under zero bias, a barrier potential is created inside the device with some specified values in terms of voltage. If it is germanium, let us take germanium material, it will be 0.3 volts. That means a potential barrier with a height of 0.3 volts is created inside the device under zero bias. Assume that is the initial condition before going into the forward bias operation. So here I am applying a voltage of VD. So whenever I am applying a voltage of VD, let us check the status of the charges here. So in the P side, the majority carriers are holes, and in the N side, the majority carriers are electrons. So here majority carriers are holes, that is connected to positive terminal of the battery. Like charges, no attraction, only repulsion. That's why here this particular holes, they has to move from P side to N side. That means they have to cross the junction in order to move to the N side. Okay. So no movement happens. Why? Because this is a positive charge and this is a positive terminal, also positive charge. No attraction happens. So that's why the hole will be moved from P side to N side. Okay. Similarly, the majority carriers in the N side, they are electrons. So here if you observe the polarity, that is a negative polarity, battery potential, and this is an electron. As you can see here, once again same charges, they won't attract, they will repel. So that's why here they won't move out of the device, they will move towards the junction. Okay, so the movement of holes must be from P side to N side. The movement of electrons from in the N region must be from N side to P side. Okay, but what happened inside the device under zero bias? A potential barrier is created. whenever a potential barrier is created, it stops further movement of charges in either ways. That means no hole will be moved from p side to n side, no electron will be moved from n side to p side. Okay, that is due to the formation of depletion region. So here I am applying a voltage of Vd, and already I said the barrier potential, the height value will be equal to 0.3 volts. Okay, so suppose I apply Vd with a value less than this barrier potential value. Okay, so here the Vd I am writing it as I am taking a value less than the barrier potential. Let it be 0.2 volts. Okay, so nothing happens inside the device. There won't be any movement of charge carriers inside the device. Why? Because a barrier potential is there which stops the movement of hole from p side to n side, electrons from n side to p side. Why? Because the applied potential is less than the barrier potential inside the device, that is 0.3 volts. Suppose whenever you are applying a value of the barrier potential, what happens here? So earlier the potential barrier is there like this with a height. Okay, so whenever the applied Vd is greater than the barrier potential value, what happens here? Slowly the barrier potential height will be decreased like this. Okay, if we go on increasing this Vd at one instant of applied voltage, this barrier potential will be diminished. No barrier potential will be there, and all the holes from p side to n side and all the electrons from n side to p side will be crossing the junction, thereby creating a larger current. I call it as a majority, I majority. Why I majority means this is happening due to the movement of majority carriers. That means majority carriers in the p side or holes, majority carriers in the n side or electrons. Holes will be moved from p side to n side and electrons will be moved from n side to p side whenever the applied voltage is greater than the barrier potential voltage. So before that, no movement of charges happens inside the device. Why? Because already a barrier potential is created inside the device. Okay, so that's why whenever Vd is less than the barrier potential, the current through the device is zero. No current will be flow, even though you are applying a forward biasing voltage. Whenever it is greater than the barrier potential only, slowly the barrier potential is going on decreasing and it will be diminished. And also here the electrons, earlier they are uncovering, now they are covering. That means slowly the depletion region is diminishing itself. So here see, due to the movement of the holes, here the coverage happens once again like this, and here the coverage happens with the electrons like this. Okay, why? Because the movement is happening from p side to n side. Where the barrier potential is not there means all the holes will be moved. Okay, so finally the depletion region will be absent like this. So concluding statement here is, in the forward biasing mode of operation, a larger current will be flown through the device. That is due to the flow of majority carriers. Okay, and the current due to the minority carriers, we ignore that. Okay, so whatever current happens inside the device under forward bias is, that is maximum current is due to the flow of majority carrier. That's why here total current, it is written like this: I majority minus Is. Is we ignore, it is very, very small. Okay, so here the forward voltage causes the depletion region to narrow. Okay, and the electrons and holes are pushed towards the PN junction, and the electrons and holes have sufficient energy to cross the PN junction. So when they acquire sufficient energy means whenever the applied voltage is greater than the barrier potential. Okay, if you observe, we discussed about three different modes of operation. One is a zero bias, second one is a reverse bias, and third one is a forward bias. So let us take zero bias. Zero bias means it happens at here only. As you can see, this is a plot between the voltage through the device diode and the current, whenever you are applying a voltage, the current through the device, it is represented by ID, and the voltage through the diode VD. Okay, let us take first forward bias. So as you can see here, even though you are applying voltage, see here 0.3 volts, I am applying 0.3 volt, but if you observe the current is still it is 0. Why? Because barrier potential is there inside the device due to the formation of depletion region. So whenever I am applying the forward biasing voltage VD greater than 0.3 volts, slowly the depletion region goes on decreasing. Okay, so that's why here slowly the movement of carriers across the junction happens. The holes will be moved from P side to N side, and electrons will be moved from N side to P side. That's why here slowly the current is going on increasing. At one instant of applied voltage, the depletion region becomes 0, and the barrier potential height will be diminished, and maximum flow of current, charge carriers happens across the junction. That means maximum number of holes will be moved from P side to N side, and maximum number of electrons will be moved from N side to P side. That's why here, as you can see, a larger current will be flown like this. Okay, and the current is represented in terms of milliamperes. Okay, in the forward bias. Okay, so zero bias is over, and the forward bias also I explained. And let us take the reverse bias mode of operation. Reverse bias mode of operation, the majority carriers does not participate in the conductivity of current. Only the minority carriers cross the junction, by which a very smaller current will be flown, as you can see here. So this is voltage, applied voltage is negative, and this is the current scale. As you can see here, the current is very smaller. That's why we are representing in terms of microamperes. Okay, so as you can see, this is called as IS. In some textbooks it is written as I0. So IS is the leakage current. The leakage current means the current flown by the movement of the minority carriers. As you can see, it is very small. This is represented by IS, as you can see. So this is the value, which is represented in terms of microamperes. If it is a forward bias, the current is represented in terms of milliamperes. Okay, and here this particular area of the curve, it is called as a breakdown. That will be explained later. So this is about the forward biasing mode of operation, and this is about the reverse bias. Okay, up to here, this is the forward bias, this is the reverse bias. In the forward bias, maximum current will be flown, and in the reverse bias, a minimum current will be flown. That is due to the movement of minority carriers. So this is represented as IS. IS means it is called as a leakage current. Okay, and the magnitude will be small. That's why normally the manufacturers represent the value in terms of microamperes. And in the forward bias, the current is very high. That's why it is represented in terms of milliamperes. So finally, I will be concluding here. First one is at zero bias, a barrier potential is created inside the device, and at the forward bias, what happens? The majority carriers cross the junction. That's why a maximum current will be flown. And in the reverse bias, the depletion region goes on increasing. That means there won't be any movement of majority carriers across the junction. So whatever the movement happens inside the device is due to the movement of the minority carriers. So that's why here a smaller current will be flown. So in the forward bias, maximum current will be flown, and in the reverse bias, minimum current will be flown. And in the zero bias, no current will be flown, but a creation of depletion region will be there, which in turn produces a barrier potential, which is represented as V0. In the forward bias, the applied forward biasing voltage will be decreasing the depletion region. That means it wants to eliminate the barrier potential. Okay, whereas in the reverse bias, the applied voltage, reverse bias voltage, it accumulates the depletion region. That means it grows the depletion region in a further manner. It improves the depletion region. That means no current will be flown. So this is about my lecture. So let me recap the things. First, I explained about the reverse bias mode of operation, and next forward bias, and next by this operating modes, I explained about the VI characteristics. Okay. With this, I conclude, and I will be continuing in the next class. Thank you.